Yes, Assalamu alaikum. Bismillahirrahmanirrahim. Actually, today we are going to discuss forward type switch for power supply. In other words, it is forward converter, forward DC to DC converter. We will take the help from the someone else notes, which is much easier to follow. Usually, these Indian guys are pretty good in manipulating these kinds of things in writings. They are very good. What is forward converter? Forward converter is another popular switch mode power supply, producing isolated and controlled DC output from unregulated DC supplies. Okay, flyback we will discuss. Mm, what is the problem with the flyback? We will discuss in the next lecture. The input DC is often derived after rectifying a little filtering of utility AC. However, the forward converter, when compared with the flyback, is generally more energy efficient and used for the application requiring negative power like 100 watt to 200 watt. Or circuit topology, especially output filtering circuit, is not as simple as in the case of flyback converter. Yeah, circuit is little bit complicated. Figure shows the topology. This is the figure. Forward converter is consist of fast switching, okay, along with a control circuit, a transformer with its primary winding connected in series with the switch and to the input supply, and a rectification and filtration circuit for the, this is a rectification and filtration circuit for the with the secondary, and load is connected across the rectified output of the secondary. The transformer used in this part is designed to be an ideal with no leakage flux, zero magnetization current, and no loss. Usually, when we are talking uh, about the thing in theory, it's the best way to ignore all the losses so that you can formulate certain mathematical models. The basic operation of this circuit is explained with the non-ideal characteristics uh, after certain modifications. Due to the Actually, due to the presence of finite magnetization current in particular transformer, we need a tertiary winding, and circuit topology has certainly a little bit changed. A more practical circuit we will see like this. Let's discuss the operation, how it is done. Actually, the figure you have seen in the previous, we have a transformer. Transformer provides isolation, we already know that. Remember this figure. It's a basically DC to DC converter with the addition of a transformer for output voltage isolation and scaling. When switch is on, input DC gets applied to the primary winding and simultaneously a scaled voltage appears across the transformer. It's a step-up transformer. Yeah, on and off. And dotted side of both the windings have a positive polarity. So this shows the dot convention. While D1 is connected in series with the secondary winding gets forward bias and the scale out input voltage are applied to the low pass filter proceeding to the load. There you go. This is the low pass filter, and this is the diode. What will happen next? The primary winding currents enter through its dotted end while the secondary currents comes out over the dotted side, and their magnitudes are inversely proportional to their turn ratio. Why inversely proportional? Because it's a step of transformer and the currents are the other way around. Thus, as per assumption of an ideal transformer, the net magnetizing ampere turn of the transformer is zero, and there is no energy stored in the transformer cores. When switch is turned off, the primary as well as secondary winding currents are suddenly brought down to zero. Yeah, it's true. Actually, this sentence is about this one. Current through the filter inductor and the load continues without any abrupt change. Okay, current flow diode D2 provides the P-Wheeling diode path for this current. Yeah, this diode is a freewheeling diode. It will, when this secondary is disconnected, then this load is discharged through this. If we keep moving, the required EMF to maintain the continuity in filter inductor circuit, in filter inductor current, and to maintain the forward bias across the D2 comes from the filter inductor itself. Yeah, during the off cycle, the energy stored in the inductor will help to forward bias this D2. During the freewheeling time, the filter inductor current will be decaying as it flows against the output voltage. But the presence of relatively large capacitor still maintains the output voltage nearly constant. Yeah, this is the very important in terms of when we have designed the chopper, DC to DC converters, buck boost. This capacitor is quite helpful in maintaining the output. The ripple in the output voltage must be within the acceptable limits. Yes, that's the design limitations. Supply switching frequency is generally kept sufficiently high such that the next turn on of the switch takes place before the filter inductor current decays significantly. Yeah, switching frequency should be so high because before the capacitor is fully discharged or inductor is fully de-energized, we should have a input from the primary. Magnitude of filter inductor and capacitor to appropriate very basic design constraints. The idea behind keeping filter inductor current nearly constant is to relieve the output capacitor from supplying large ripple currents. Yeah, you know that the issue is that the capacitor always provide an inertia current when it sees a short circuit. So as per topology, inductor and capacitor together share the load current drawn from the output. Under steady state conditions means DC current supplied by the capacitor is zero, but capacitor still supply ripple current. For maintaining constant load current, inductor and capacitor current ripples must be equal in magnitude but opposite in sense. Capacitor with a high value ripple current ratings are required to have much less equivalent series resistor and equivalent series inductor, and they are bulkier and costly. So equivalent series resistor and equivalent series inductor of a practical capacitor causes ripples in DC output due to the flow of ripple current through these series impedances. Since the output voltage is drawn from the capacitor terminal, the ripple in the output will be less if capacitor is made to carry less ripple currents. Yeah, pretty important. This message, this paragraph is very important in viewpoint of uh, quality of the output. We need to utilize the capacitor as low as we can, because capacitor always provide electric current with the ripple, and if you want to reduce it, you need a series inductor and resistor. And if you incorporate these things in the circuit, then of course your circuit will be bulkier, which is against the tradition which is followed these days. Your circuit is as smart as possible. Now, for better understanding of the steady state behavior of the converter, circuit operation is divided into two different modes, mode 1 and mode 2. Mode 1 corresponds to the on duration of the switch, and mode 2 corresponds to the off duration. Let's discuss this mode one by one. Okay. On state voltage drop of the switch and diodes are neglected. Similarly, the leakage current. For the off-state devices is assumed leakage current through the off-state devices is assumed to be zero. Switching on and off times of the switch and diodes are neglected. Actually, we are considering the ideal conditions. Under the ideal conditions, losses and switching losses are there. And also transformer is assumed to be ideal with no magnetization current, no leakage inductance, no losses. And the filter circuit elements like inductor and capacitors are assumed lossless, which is not true. But for the ideal conditions, for the simplified steady state analysis of the circuit, the switch duty ratio is defined in the previous chapter. That's the duty cycle. Input and output AC are assumed to be constant and ripple free. Current through the filter inductor is assumed to be continuous. Actually, this is not the case. For that purpose, you need to attach a very highly inductive load or highly inductive, because to make the current continuous, otherwise it will make some different scenario. Let's discuss the mode 1. In the mode 1 of the circuits, after switch mode 1 of the circuit starts after switch S1 is turned on. Okay, come back over here. Switch is on. No current is flowing through the circuit. This connects the input to the primary winding. Both primary and secondary start conducting. Yes, of course, when it is current is flowing through. This is energizing and is a mutual inductance, and the secondary winding is also energizing. Primary and secondary winding currents are related to their current turn ratio. That's for sure. Voltages and currents. Now we can see that in figure 223.2a shows in bold line the current carrying path of the circuit, and we shows the functional mode 1. This is your mode 1, and the bold lines show the current carrying path. This is the bold line, this is the bold line. Okay, as switch closed, diode D1 is in the secondary circuit gets forward biased. Okay, and the input voltage scaled by the transformer turn ratio is scaled by this gets applied to the secondary, and diode D2 doesn't conduct during mode 1 as it remains forward reverse bias. Yeah, of course, the positive voltage is over here and it is reverse bias. As can be seen, the output circuit consisting LC filter. Okay, this is the LC filter, and load gets a voltage equal to this one. Yeah, actually this is the conversion ratio, and voltage is shown across point P and N in the figure 2.23.2, and its maximum achievable across the load corresponding to the delta 1. Okay, We already discussed this delta. UT ratio. Mode 1 can be called as powering mode, during which the input power is transferred to the load. Similarly, mode 2 is called as a freewheeling mode. Yeah, starts the turning of the switch. Let's see what happened in the mode 2. During the mode 2, as soon as the switch is turned off, primary and secondary winding currents of the transformer fall to zero. Surely, you can see the bold lines. The only the current switch is off. D1 is off. What happened? The inductor which is charged with this polarity. Now the polarity of the inductor has been reversed. The inductor tried to retain its charge and switches its polarity. Now negative is over here and positive is over here. As compared to the previous case when the switch is on, positive is here, negative is here. However, the secondary side filter inductor maintains a continuous current through the freewheeling diode. Of course, it is energized, and when it is reversing, then it has a flowing path through the load. And from D2, diode D1 remains off during this mode and isolates the output section of the circuit from the transformer and then surely this diode will provide the isolation. It doesn't allow the current to go back to the other side by mutual induction. This is the complete explanation. The bold lines shows the current flowing paths, and this is the mode 2, and diode is shorted because it's conducting. The inductor current continues to flow through the parallel combination of load and the output capacity. Yeah, it keeps on flowing. There is no power flow from source to the load, but still load voltage is maintained nearly constant by the large output capacitor. Since the capacitor is charged during the on cycle and load and capacitor are in parallel, and the capacitor voltage, whatever is on capacitor will be appear across the load, which kept constant with a large capacitor value. Large capacitor and inductor provide continuity in the load voltage. That's true. However, there is no input power during the mode 2. The stored energy of the filter, inductor and capacitor will slowly dissipate in the load. Hence, during this mode, the magnitude, the inductor current and capacitor voltage will be falling slightly. In order to keep the load voltage magnitude within the required tolerance, the switch should be turned down again to end the freewheeling mode and start the next powering cycle, that's the mode 1. Under steady state, loss in the inductor current and the capacitor voltage in mode 2 is exactly made up in mode 1. It may be difficult to see that to maintain load voltage within the desired tolerance band, the filter, inductor and capacitor magnitude should be sufficiently large. Yeah, that's what true. If you want to maintain a constant voltage, you need to do these things. It may not be difficult to see that we need a large value of inductor and capacitor. However, in order to keep the filter cost and its physical size small, these elements should not be unnecessarily too large because large value capacitor has a very large size and inductor also keeps size issues. For faster dynamic control over the output voltages, the element should not be too large. May be pointed out here that the filter, inductor, capacitor, transformer, and heat sinks for the switching devices together account for nearly 80% of the power supply weight and the volume. Yeah, these are the actually main components which uh, cover all everything from these uh, weight and volumes are usually covered by inductor, capacitor, and transformer. Heat sinks is another party. So we have understood the principle of mode 1 and mode 2. One important factor is directly influences the size of the filter elements and the transformer is the converter switching frequency. Yeah, that's a valid mode. And in the first lecture, very first lecture, I explained that if you keep on increasing the frequency, your transformer and filter size is going to be reduced. There is some relationship between the number of turns and the frequency. High frequency operation of the switch will help in keeping the filter and transformer size small. Switching frequency of the typical forward converter may thus be in the range of 100 kHz or more. The higher end limit on the switching frequency comes mainly due to the finite switching time and finite switching losses of practical switch. Yeah, there is a trade-off when you keep on increasing the frequency, then there is a switching loss, which is also you need to take into the account. Now, switching limitation has been ignored in the simplified analysis, as between the switch and the diode has assumed to be ideal with no losses and zero switching times. Control over the switch duty ratio, which is the ratio of the on time to the on off time, provides a control over the entire element. Now, this is called the duty cycle. The on time actually means beside this. And there is a relationship between the output and the input voltage we need to be taken into account. Yeah. Look at the mode 1 and mode 2 and output ratio with the assumption of the constant input output voltage. The instantaneous value of the inductor voltage during mode 1 can be written as, yeah, this is the transfer ratio minus this one. This is true inductor voltage. Yeah, input coming from the primary minus the output voltage across the load. And this is what we see during the mode 2. The inductor voltage is inverted. This is minus V naught. Since voltage across an inductor average over a steady state cycle must always be zero, this sum should be zero. And after simplifying this, we have this ratio. Output is duty cycle into the transformer foundation. The most important thing is the output voltage is only valid under the assumption of continuous inductor current. Okay, this is pretty simple. It's, under the discontinuous inductor current, the relationship between output voltage becomes non-linear and load dependent. Yes, you need to be careful about this calculation. And I think that this is the more typical circuit for the uh, practical forward converter. It has an additional winding over here, and this is called bifilar winding. Bifilar windings usually withstand large electrical voltage stress, and it is faster than the typical scenario. Yeah, this is all about the switch mode power supply. This is called forward switch mode power supply. And if you are interested in this topic, I will share the notes with you, and you can go through the rest of the topic by yourself. Uh, yeah, thank you very much.